Thanks for coming. I'm going to tell you about work that my group is doing in the area of printed electronics. And I thought I'd start by showing this lovely image and asking whether anybody knows what this invention is that's depicted here. Anybody know? Yes, it's what?
Printing press.
It's a printing press, right? It's the Gutenberg printing press, which was developed in Germany in the mid 1500s. And you know, this was a revolutionary invention because ultimately it allowed dissemination of books to the general population at reasonable costs, and then also spawned the formation of the newspaper industry, right? So before the printing press, you know, access to books which were handwritten was very limited, and there wasn't really anything like the free press because there was no way to generate large numbers of copies of printed matter. So, you know, this had a profound impact on society, and in the last 600 years, printing has become a ubiquitous and very advanced technology. We benefit from printed matter all the time, packaging in grocery stores. You go to the mall, you get elaborately printed shopping bags and so on. So it's not just about printing magazines and newspapers. And this is another example of that. If you want to purchase ceramic tile for your kitchen or your bathroom, chances are the patterns that are on the tile have been inkjet printed in large printers containing thousands of nozzles, and the ceramic tiles go into these machines. The ink is printed, and then there's a glaze put over it, and the whole thing is fired to set the ink. So this is, you know, a manufacturing process based on printing, and this idea that we can use printing for manufacturing is really spawned a lot of interest in whether one can use the similar techniques to print circuits. So there's groups all over the world interested in this. There are now electronic inks, and I'll talk a little bit about this. So inks based on semiconductors, insulators, and metals. And the idea is that you'll load these inks into printers, maybe inkjet printers, maybe aerosol jet, maybe gravure printers. There's a variety of graphic arts methods to pattern the inks onto surfaces to build up electronic circuitry. And the motivation for doing this is in part the kinds of new applications that you can get if you put circuits onto flexible substrates. So you can imagine making unbreakable displays, new kinds of lighting motifs, integrating solar cells into backpacks and tents and so on, or various kinds of wearable sensors. There's a lot of interest in industry in the Internet of Things, so basically integrating electronics into packaging for automatic inventory tracking and so on. And then wearable electronics, as you know, is of course a growing trend. Applications I like are distributed sensing in bioelectronics and also in robotics. If you think about trying to record very precise EEG signals, so brain signals, you know, this is obviously a very cumbersome way to do it. You'd like some kind of skull cap that allows you to be more mobile, for example. And these kinds of devices would be useful in diagnosing sleep disorders, for example. So we're thinking about applications where you want to put electronics over large areas, all right? Anything that you can do with a silicon microchip, you should do with the silicon microchip. But silicon is not good for covering large areas. And so that's the kind of application that looks promising for flexible circuits. Okay, so there's another motivation, though, for printing besides getting things on flexible substrates. In principle, printing is a greener, more environmentally friendly process because it's additive. So if I want to put two metal lines on a substrate, I just draw them with my printing process. In a conventional fab, like if you go over to the MNC next door here, you would put down a metal film, and then you would go through a bunch of steps that effectively etch away the vast majority of the metal to produce the two lines. So this is a subtractive process. Printing is additive, and therefore there's less waste. So that's another attractive aspect of printing. And so the big picture in my mind is that we combine additive manufacturing with continuous roll-to-roll processing to achieve lower cost per unit area. But of course, it's not just about cost. It's also about the new kinds of form factors you get when you put electronics on flexible substrates. So those are the big drivers for this area. And so now what I want to do is talk about the challenges and some of the things that my group is pursuing to address the challenges. So obviously, there's an important materials challenge. We always need better electronic inks. All right? And it turns out there are commercially available inks now based on conducting polymers, various kinds of metals, so you can buy these. You can load them into pens. You can draw simple conductive lines for demonstration purposes. But of course, to make active circuits, we're going to need really high-performance semiconducting and insulating inks as well, and that sort of requires a whole nother level of materials development. And in this respect, there's overlap with my long-term interest in organic semiconductors. These are molecule-based materials, pi conjugated, so lots of double bonds, that are soluble, that can form the basis of inks. So, for example, this material here is a polymer semiconductor. It's soluble in various kinds of chlorinated solvents. And you can load it into an inkjet or aerosol jet printer, and you can actually print solar cells. You can print transistors based on this. So what's nice about this is this material can be processed at room temperature. So most inorganic semiconductors, if you deposit them from solution, they still have to be annealed. And the annealing temperatures are typically 400, 500 degrees centigrade. If I have a plastic substrate, the substrate can't survive that temperature. So what's nice about organics is that they can be processed near room temperature, which opens the possibility up of using plastic substrates. So that continues to be a theme in my group, working with these materials and understanding the physics of their transport, and that's not the subject today. But these are certainly enabling materials for printed electronics. I want to switch, though, and talk about processing, because that's really where we focused most heavily. And this is work I do with Lorraine Francis. So one big challenge is the resolution of printing. So here is printing speed versus minimum line width or feature size that you can print. Conventional printing processes are very fast, but they tend to be poor resolution. So printing newspapers, you only have to print features maybe 100 or 50 microns, and that's essentially invisible to your eye. So the width of one of your hairs is about 100 microns. So that's the kind of feature size that we can achieve using conventional methods. But for electronics, we want to be down here in the 1 micron regime. So we've got this big empty space here, and that's the challenge. How do we go from this region to this region? So that's challenge number one. The second challenge, and the one that I think is actually really the biggest challenge, is ink registration. So I don't know if you've ever gotten a printed material. In newspapers, this used to be very common, that you would get the comics section on Sunday, and the red and blue inks would be out of registration, and so your favorite comic strip would be kind of blurred out, right? Well, that's an issue of alignment or registration, and the issues are super important for making circuits. So if I imagine a continuous process where I'm printing a metal and a semiconductor and an insulating ink, of course I want these to be in very precise registry, because I'm trying to build up a thin film device. It doesn't matter what this is. Just imagine I'm trying to make a stack of materials that looks like this, but I'm somehow misaligned and I get this. Well, this device doesn't work, right? And the key thing is that the dimensions here are a couple of microns. So the precision that I need is a micron or better. And I want to do it on a continuously moving substrate. And the substrate is subject to thermal stresses because of the annealing and baking steps I have in here. And besides that, it's inherently deformable. So I have a deformable, moving substrate, and I want registry of multiple layers of ink to a micron or better. That, I think, is a giant engineering challenge, and something that Lorraine and I have been very interested in. And it occurred to us that what we really need is some kind of process where the registration is just locked in from the very first step, that we have what we would call a self-aligning process. So we do some kind of patterning in the beginning, and then all registration of inks is sort of automatic after that. That's the kind of thing we're looking for. It's called a self-aligning process. So we've developed such a process that's now patented. So we had a very good student who's now working at 3M. His name is Ankit Mahajan. And together we developed a process we call the scale process, self-aligned capillarity-assisted lithography for electronics. It's a mouthful. But the basic idea is this. We're going to emboss plastic substrates with reservoirs, capillary channels, and device cavities. And they could be multiple levels. All right? We're going to do this in one imprinting or embossing step. And then we're going to use inkjet nozzles to deliver inks just to the reservoirs, which are easy to hit, rather large dimensions. And then we'll use capillary forces to spontaneously pull the ink out of the reservoirs and into the device cavities. And if we do this right, so that everything is encoded in the first imprint step, all we have to do is deliver the right ink, metal, semiconducting, or insulator, to the right reservoir at the right time, and we'll build up multi-layer devices. That's the concept. So it solves the alignment issue, but it also solves the resolution issue, because imprinting can be very high resolution. You can imprint hundreds of nanometers feature sizes, and so that's far better than anything you can do that you can just print directly. So we solved the resolution problem, we solved the alignment problem. It's still additive, we're just putting the ink where we want. We think that it's scalable and parallel, so we can have banks of inkjet nozzles delivering inks to many reservoirs at the same time. And I'll show you, we're trying to implement this roll-to-roll so that it's truly high throughput. So here's a reservoir and some imprinted capillaries. And what's happened is a drop of ink has gone into the reservoir, and immediately capillary forces have drawn the ink out. And because of refractive index matching, everything became invisible. But when the ink dries, you can see the channels again. So this is just to show you that the capillarity is fast, it's rapid, it's spontaneous, and we can get very high resolution features this way. So what does this process look like roll to roll? The first step, we have a roll of plastic. It's called the web. All right, so a continuous sheet of plastic is called the web. So this might be a polyester web. We coat it with a UV curable or UV cross-linkable material. And that's done by typically a reverse gravure process. We take this wet web and we bring it into contact with a stamp on a roll. And that stamp has all the features that we want to make. And while the stamp is in contact with the web, we fix the pattern with irradiation with UV light. So essentially, we're almost doing a micro molding process right there in the contact region. The stamp displaces the liquid, and then the liquid is solidified by means of the UV light, so that we create imprinted patterns. We can have raised patterns, we can have depressed patterns, we can have multiple levels in one imprint, and we're going to roll that up. That's step one, the imprinting process. Step two is taking that roll, and now on a different line, we start to deliver inks by inkjetting into the reservoirs. After each delivery, we need to do some kind of annealing or sintering step. That can be done with a conventional oven, it can be done with IR lamps, it can be done with blasts of UV light, depending on the material. So we're going to deliver different inks, again, to different reservoirs, and that will create the devices, and that's the process. So we actually have two roll-to-roll lines on the ground floor of this building. This is the heart of the imprinting line. So what you see are stamps that are made out of PDMS rubber. They're wrapped on this roll. We bring the wet web into contact. There's a slab illuminator that cross-links the liquid material underneath, and then we strip off the web on the other side with the imprinted features. This line is about 14 feet long. It just does the imprint step. We have a second line that does the material delivery, the inkjet delivery step. Right now we can do this process at about 50 centimeters a minute, something like that. Ultimately we'd want to run at meters per minute. So, okay, I've outlined the process, but now, we get down to the nitty-gritty. Can we actually print a whole circuit? And this is a very simple circuit that we made 5 years ago by a serial technique called aerosol jet printing. And it doesn't really matter what it does. The point is that we have to be able to make all of these building blocks, resistors, transistors, capacitors, and in principle we also need diodes, and of course we need metal lines, which are called interconnects. These are the building blocks of all circuits. We have to be able to make all the building blocks extremely reproducibly. If we can do that, then we can actually start to build systems on plastic. So this is very much the stage we're in now, is can we make all of these building blocks? Right? And I have several graduate students that I'll acknowledge at the end who are working on these problems. So let's just think about metal lines or interconnects. How would we make such metal lines by the scale process? So we would imprint, let's say, a very simple feature, 2 reservoirs and a channel. We then deliver ink to the reservoirs. Capillarity draws the ink in, and when the ink dries, here we have a skin of silver on this trench. And what we really want is a solid metal line, right? And so what we need to do is plate up. And so we can immerse this substrate in a copper plating solution and plate up bulk copper, which is what's been done here. And this allows us to make very low resistance lines. And the thing I want to point out is the aspect ratio here. This is a little bit underdeveloped, but this is roughly maybe 10 microns by 15 if I go all the way up here. The point is that it's a roughly 1-to-1 aspect ratio. If I just took inkjet printing and printed on a flat plastic substrate, I'd get a 20 to 30 micron wide line, but after it dried, it would be like 100 nanometers tall, right? So it'd be a very broad, very shallow structure. We can actually make structures here that look like, respectable current conductors. Okay, how would we make a resistor? That's pretty simple building block. We have to be able to make them. So we might imprint features that look like this, 2 reservoirs and a corral. We drop ink into the reservoirs. That gives us these electrodes here. Again, capillarity draws the ink into these channels. And then we'll drop conducting polymer to connect the 2 electrodes, and that's our resistor structure. We can tune the resistance by tuning the thickness of this film, by tuning what material we use. We can also use carbon black, for example. We can also tune the resistance by changing the spacing between the electrodes. And this has allowed us to make resistances that vary from an ohm to mega ohms. And we can print them on plastic sheets, full arrays of them with 100% yield. If you characterize them, you would expect Ohm's law behavior. This is current versus voltage, and sure enough, beautiful linear curve. We can wrap them around a mandrel and measure the resistance as a function of how many times we bent it and what the strain is, and we can see that you exert tensile strain in this case, tensile bending strain, and the resistance seems to be robust to multiple bending cycles. So resistors look pretty good. I'd like to share with you that there's some interesting fluid mechanics associated with this process that we can take advantage of. So there's some science here that's kind of fun. So we can imprint structures that look like this, and this will turn out to be useful for us. It's a deep, wide trench connecting to a shallow, narrow trench. And that junction turns out to rectify fluid flow. So if you look on the top here, the fluid that comes from the small channel, moving from left to right, it gets stuck. The fluid gets pinned right at the junction. But for flow going from right to left, from the big channel to the small channel, it passes through. All right? And that turns out to be extremely useful in several ways for us. We need ways to control the flow. And this is basically a passive fluidic rectifier. So this works on a variety of different inks. So if we use silver ink, here's the stopping direction, here's the pass-through direction. Same with conducting polymer ink. This is a material called PDOT. This is a semiconductor, P3HT. It works, and it works for a wide variety of viscosities. So here's how we can use this in fabrication. Suppose we make a structure like this, imprinted. We can deliver silver ink to reservoirs that are not shown. The silver flows and stops right on these edges. Then we deliver conducting polymer ink to a reservoir up here, and we get a nice connection here. So now we really have things that look well defined, something that an electrical engineer would respect. And we can control the length of these resistive channels, of course, very precisely by the initial imprint pattern. Here's resistance versus length, and it does exactly what you would expect. Scales linearly. So that's a simple example of how we use this diode, but there are other ways. So for example, suppose I'm printing a device here, and I'm printing a device next door to it. And suppose I want them to be connected, but while I'm building them, I don't want crosstalk of ink. So if I make diodes there, I can build this separately, and then at the end short them together by delivering, let's say conductive ink that flows the other way and connects the two. So this diode structure turns out to be really wonderful, and you can ask yourself, well, what's going on? Why does it even work? And there's something called the Gibbs Criterion, which basically says fluid gets stuck at edges. That's well known in fluid mechanics, until you hit a critical angle, all right? So there's force balance arguments that say this drop will not go over this edge until I exceed this critical angle, all right? And so what we've done here in these channels is in 3 dimensions, we have made edges. So we have sidewall edges, but we also have an edge at the bottom, right? So the 2 edges, the 2 sides and the bottom all have sharp edges. So if we consider flow in this direction, what's driving the flow is the curvature here, which gives us a capillary pressure, right? The pressure, because of the surface tension, the surface is pulling on the liquid here. This liquid is at slightly lower pressure than the pressure in the reservoir. And that delta P is the capillary pressure which drives the flow. So as long as I have curvature, I'm going to get flow. But what happens is I come up to the edge and I get this pinning effect. Well, the flow keeps happening because I have curvature, but then the interface flattens out. When the interface flattens out, the capillary pressure goes to 0. There is no more driving force for flow this way, but I also haven't hit the critical angle. So I just arrest the flow, right? Because I haven't hit the critical angle. On the opposite case, when I come from the big channel, from the right to the left, the way this works is the liquid comes around and it gets stopped at this edge, but because of the geometry, I still have massive curvature here, and I have a driving force for capillary flow, which continues to drive the liquid. Well, what happens is the liquid keeps flowing, and before the interface flattens out, I hit the critical angle. And so it just bursts through. It just passes right through. So it's a very nice piece of fluid mechanics, which turns out to be really useful to us. Okay, back to devices. We can make capacitors. Here's one design, interdigitated electrodes. We used graphene ink for the electrodes. They're interdigitated like this. We drop a gel electrolyte in there that gives us a capacitor. If I have a resistor, which I showed you we can make, and a capacitor, I can make an RC filter. So I look at the voltage out as a function of AC voltage in, and some of you may recognize this is a low-pass filter. This is output voltage versus frequency. The cutoff frequency here is just tuned by what I print for RNC. All right, and we can move this knee around as we like. So how am I doing on time here? Maybe 5 more minutes. The big prize in this business is to make transistors, which are the fundamental switching element in circuits. And these are 4-level structures, and so they're inherently harder to make. So the basic thin film transistor structure consists of a gate, an insulator, a semiconductor layer, and 2 electrodes, the source and the drain. The idea, of course, is that you apply a voltage between the source and drain and try to push current through, but the amount of current is regulated by the gate. Basically, the gate is capacitively coupled, and when the gate voltage is on, I have accumulation of charge in the semiconductor. When the gate voltage is off, I have no carriers and I have no current. So we want to be able to make this. It's a 1, 2, 3, 4-level structure. How do we do it? Well, first let me tell you that we have a brand of TFT that we call an electrolyte-gated transistor, EGT, and my group works a lot on these. This is the basic design is the same as what I just showed you, but the insulator material, so this would be the source, drain, here's the semiconductor, and this is, we're not talking about single molecules between electrodes, right? This is 10 microns. This is a film of this material, but this dielectric is actually a gel electrolyte. So when we polarize it, the ions move And we get electrical double layers here, which charge the semiconductor and turn it on. All right? And the only point I want you to take here is that we do this because the capacitance of electrolytes is enormous, and that gives us low voltage operation, which I'll show you. So here's our EGT design, semiconductor, source, drain, and it turns out because we use an electrolyte, we don't have to have the gate aligned over the channel. We can put it off to the side. If you've done any electrochemistry, this is intuitive, and if you haven't, it's maybe strange, but it works. So that's nice, and it makes the fabrication easier. So this is just an outline of our TFT process. Again, we start with a UV curable polymer on plastic. We stamp into it. These stamps are made in the clean room. So I didn't mention this before, but my students spend a lot of time in the clean room patterning silicon wafers that's the master pattern. Then we make a rubber copy of the master, and that's what gets wrapped on the roll for doing imprinting. So we use conventional fabrication techniques to make the stamp, but then we're going to use this stamp over and over and over again. We're going to then deliver inks into this multi-level pattern in the right sequence. So let's see how this works. So this is a multi-level imprint. You have 1, 2, 3, 4 layers here. You can see approximate dimensions. This is an actual image of an imprinted pattern. We then start to deliver inks. So metal lines are fabricated this way. This is the cross section through here. So these are focused ion beam cuts where you can see the nice silver coating in these trenches. And here is a perspective by SEM of what the channel looks like. Then we deliver a polymer semiconductor. Again, it can be processed near room temperature, which is nice. That coats the electrodes. Then we deliver a conducting polymer, which is the gate, and we use this pinning effect to actually split the flow. The flow bifurcates and runs north and south in this way. And you can see here's what we call the stopper. That's this trench here, and you can see maybe the conducting polymer electrode that's run along this edge here. So that's our side gate. And then we flood with gel electrolyte. And those are our devices, and I'll show you the IV characteristic. This is the current flowing from source to drain, log scale versus voltage we apply on the gate for a 0.8 volt bias between the source and the drain. And what I want you to see is that we have 6 orders of magnitude change in current as we go from 0 volts to a volt. It's a switch, and it's really low voltage, and it's entirely printed. And we can make all arrays of these, and they have all the IV characteristics that you would expect for a transistor. So where do we want to go from here? I haven't showed you diodes, but we're working hard on diodes. And so the idea is once we have building blocks, we go to actually building systems on flexible substrates. So these could be amplifiers, they could be wearable radios, they could be various kinds of sensors for robotics, backplanes for displays, maybe sensors for healthcare monitoring. And so that's where I'd like to wrap up. I need to acknowledge the people who do all the work, in particular my current students who work on this project. Motau is co-advised, and Christopher is co-advised with Lorraine Francis. I need to acknowledge her. And Lorraine and Satish Kumar and I have a grant that funds collaborative work in this area. I've worked with these faculty as well, and then these are former students and postdocs who've worked on this project. The funding has come from the Navy and the National Science Foundation and what we call iPrime here. So thank you.